Engine defect is one of the causal and indicative factors in aviation accidents. According to the statistics from the International Air Transport Association, the global aircraft accidents rate was about 0.97 per million departures from 2016 to 2020 under the monitoring program of IATA Operational Safety Audit, and the total accidents involved undesired aircraft state and related to engine failure was about 4%. Although this kind of event may have an extremely low probability to happen, but with aircraft safety, we assume if anything can go wrong, it will go wrong, and it may cause an extremely problematic situation once it occurs. As an example, in May 2019, an airplane had just taken off, and the flight experienced an abnormal situation during the climb phase in which one of the engines went amiss after approximately 17 minutes. The flight crew detected a vibration in engine number 1. According to the report from the Taiwan Transportation Safety Board, the probable cause of the increased vibration was the deterioration of a seal, resulting from an increase of localized heat. The air oil seal is a critical component in the compressor rear frame. This type of seal has a labyrinthine design and it is commonly used. It is typically comprised of the following: a rotary seal with blade-like fins and a serrated outline in the cross-section of the rotor shaft, a stationary seal, a corresponding abradable layer that builds with the honeycomb structure or plasma sprayed coating as the lining of the stationary material, and the designed flow passages for air pressure to separate two types of functional fluids from different sectors. Upon the initial running of the engine, the tips of the fins rub against the abradable lining. So, this abradable lining is also called rubland. If the labyrinth seal is used in bearing chamber seals, it prevents oil leakage through allowing pressurized air to flow from the outside to the inside of the chamber. As the pressurized air passes through a series of fins, the air pressure decreases considerably, restricting air to flow from one side of the seal to the other. The stationary and rotary seal will introduce extra contact rubbing between the fins and the rubland. If a considerable amount of the relative central axis deflects during rotation, excessive heat is generated subsequently. The localized heat accumulation can lead to the thermal degradation of the material properties, which initiated the failure of the seal structure in this instance. The failed air oil seal structure was deformed and struck off by rotating parts. The resulting debris shattered radially because of the centrifugal force. This resulted in a series of impacts on the adjacent parts and damage to the upstream related seals. The dynamic balance of the pressurized air flowing in the air passages was interrupted and caused a malfunction of the air seals. High pressure and high temperature air seeped directly into the oil sump chamber. The vaporized and ignited oil was squeezed into lower pressure air passages, or was pressed forcibly by the highly pressurized air, and was expelled out of the sump from the broken breach on the air oil seal. This caused the engine to lose most of the lubricant in the next few seconds. Following that, the flight crew received an engine 1 oil quantity low message and an engine 1 fire warning at flight level 250. There are two types of key components in this area: the roller and ball bearings in the oil sumps of the engine. These bearings endure most of the moment of inertia in this zone and act as the interface between the inner rotary shaft and outer stationary structure to maintain the rotational stability smooth operation of the engine. Engine operation with the above-mentioned insufficient lubrication caused severe thermal damage to the bearings. This resulted in the massive engine vibration that the flight crew detected. It is worth noting, however, that this abnormal engine vibrational behavior could still have been mitigated, if necessary, through other aviation safety management mechanisms. Pilot responses to such failures in engine operation are regularly tested, and it is an inevitable subject during proficiency checks for assessing and retaining pilot licenses. Engine fire is one of the key subjects for which pilots are trained and tested as a part of their annual flight simulator program. which aims to reduce the threats of accidents or serious incidents based on the lessons learned from historical catastrophic events. This testing enhances the situational awareness of flight crew during unexpected and poor operating conditions, their decision-making abilities in such situations, and their execution of standard procedures to deal with abnormal events in a disciplined manner. The flight crew shut down engine number 1 according to the standard procedure at flight level 250 and discharged the fire extinguishers as per engine fire procedures. In the meantime, the flight crew declared a Mayday emergency to the air traffic control and performed an air turn back immediately. The flight was operated under emergency conditions with a single engine operation for approximately 40 minutes. And the flight crew prevented an issue from becoming a crisis. All of the passengers had a safe landing. The risks and threats from this engine fire were mitigated in this case due to the appropriate responses and safety defense mechanisms used to handle the situation correctly. And yes, if anything can go wrong, we assume that it will go wrong. However, the unknown risks and threats can be handled in the appropriate manner through adhering to proper training and following proper safety guidelines.